Elastic potential energy in a stretched wire. When a wire is put under a tensile stress, work is done against the interatomic forces. This work is stored in the wire in the form of elastic potential energy. The amount of work done W in increasing the length of the wire from L to L plus L, that is from L equal to 0 to L equal to L is, so we all know that work done is equal to force into displacement. Okay, so the Young's modulus is given by stress by strain, that is force by area divided by change in length by original length. If you simplify this equation for force, you will get Young's modulus multiplied by area of cross section of the wire, change in length by original length. So that's what is substituted here in this equation. So YA, this change in L, del L is nothing but L divided by L. So this is force into displacement, which is dl. So work done is, if you want work done, you have to integrate from 0 to L. If you see the picture clearly, this is the original length. On application of the load to this wire, there is a change in length, which is called as del L or small l. So in the place of del L, we substitute small l. That means if you take this as the reference point 0 and this as L, you have to integrate from 0 to L. So in this integration, the force into displacement gives work done, and you are integrating from 0 to L. Okay. Having understood this, now we have to go for integration. If you see, it is with respect to dl. So YA and L are constant. If you integrate L, it becomes L square by 2. And you have to substitute the limits, upper limit as L and lower limit as 0. So that's what we are going to see in the C. Okay. Now, YA and L is constant. Upper limit is L, lower limit is 0, L dl. If you integrate this L with respect to dl, it becomes L square by 2. Now substitute the upper limit L for this equation, and upper limit minus lower limit. Minus lower limit, if you substitute 0 for this, it will be 0 only. Therefore, we have YA by 2L into L square. Now if you carefully watch, the half is written as it is 1 by 2, Y is there, A divided by L, L square. So L square, but this becomes L square. You have two capital L. So one capital L and this will get cancelled. Therefore, you will get the previous equation. That is, this equation and this equation are same. Now, why we do this? We want to get a simplified answer that is easy to remember. So now we can write work done is equal to half Young's modulus, change in length by original length, which is nothing but strain, square, therefore square, area into length. Area into length is nothing but volume of the wire. Okay. Now this once again can be written as W is equal to 1 by 2. Young's modulus, you know, stress by strain. It is the ratio of stress by strain. So here one strain and this square will get cancelled. Therefore, we have a simplified result which is easy to remember. 1 by 2 into stress into strain into volume of the wire. So now we represent this work done in symbolic notation. So work done is equal to half into sigma. Sigma is represented for stress and epsilon is represented for strain into volume of the wire. Now if you bring this volume of the wire, you will get the elastic potential energy per unit volume. That means this volume of the wire, W by volume of the wire, gives the elastic potential energy per unit volume of the wire U. Therefore, the elastic potential energy per unit volume of the wire which is given by U is equal to 1 by 2 into sigma into epsilon. So this is very easy to remember, which is 1 by 2 multiplication of sigma is stress, epsilon is strain, and this U is nothing but elastic potential energy per unit volume. So that's all about this topic about elastic potential energy in a stretched wire. Hope you have understood this topic. Thanks for watching. Nandri.